Viewers like you make this program possible. Support your local PBS station.
Today, more people are living or working in tall buildings than ever before. Population surges in some regions, economic prosperity in others are seeding the world with tall buildings.
The real driver for tall buildings are the twin effects of population growth and urbanization.
But if the sky is the next frontier for human life, this raises a crucial question. Are tall buildings as safe as they could be? And if not,
oh my God,
how can we make them safer?
right there.
There have been horrific blazes in tall buildings here and across the globe.
When there's a fire, one thing that unites rich and poor, they all die the same way.
Outside the U.S., earthquakes have felled tall buildings and killed indiscriminately. Could cities like San Francisco be next?
It's not if, it's when.
Shut off the gas! Shut off electricity!
And some tall buildings may go down.
That is what our modeling tells us.
Can the latest generation of tall buildings meet these and other challenges, even as we build more of them?
Skyscrapers today, especially the tallest ones, are very safe buildings.
But mistakes can still happen.
Downtown high-rise sunk 16 inches.
And beyond making them safer, is anyone making them more appealing?
We want a different model for organizing office buildings with constant movement, flow, and interaction.
It's just an amazing building.
Few structures in the modern era have had a greater impact on the way we live or work. And now the question is, can we make them even better? High risk, high rise, right now on Nova. Skyscrapers are among humankind's most awesome and extravagant achievements. Engineering marvels so tall and strong, their very existence seems to defy the laws of physics. The most daring skyscrapers are essentially showpieces designed to attract elite businesses or wealthy homeowners. Architecturally, these tallest of the tall exhibit the extreme of what is possible. But it is tall buildings of all sizes that are today filling many of the world's cities. And for good reason.
United Nations statistics show that there are almost 200,000 people urbanizing on this planet every day.
And the only true way to address it is going up in height.
If you build taller, you could pack more people onto the same address.
Without tall buildings, it would have been virtually impossible to accommodate urban population surges in Asia and the Middle East.
You see in countries like China and India, cities which have gone from 2 million to 20 million in one generation. And so that certainly generates a need for building stock to house that density.
In the U.S., the pressure to build tall is centered in cities benefiting from the uptick in the global economy. But as most major cities become crammed cheek to jowl with tall buildings, as we spend more of our lives looking down on the world below, will we begin to lose our sense of place, of neighborhood, of community? Or can tall buildings begin to embrace a more humanistic vision, one that stresses livability, interactivity, and eco-responsibility? Some designers are certainly trying new ideas. But as we build skyward at a staggering rate, there's a more basic question. What have we learned over the decades about making tall buildings as safe as they can be? Can we ultimately trust them with our lives? Many American cities are identified by their iconic skylines, and seeing new skyscrapers join older ones seemed inevitable, right up to 9/11.
After 9/11, most people said this is the end of the skyscraper, that people will be too afraid to live in them. They'll be too afraid to work in them.
Certainly many people in the profession believe that it'd be the death of the tall building.
Even Bill Baker, one of the world's foremost tall building engineers, had his doubts.
I thought that my specialty was over, that it was going to be the end of tall buildings. And then, but quite remarkably, soon thereafter, I was designing the world's tallest building.
That building is the Burj Khalifa in Dubai, largest city in the United Arab Emirates. As the world's economy began to rebound after the financial crisis of 2008, the drive to build tall in wealthy urban centers became a global trend.
Let's be clear on this, there's been an explosion of the number of tall buildings around the whole world being built.
Anthony Wood heads the Council on Tall Buildings and Urban Habitat.
They showed tallest 20 in 2020, which we did about 6 years ago.
The organization charts the rise in tall building construction and classifies the world's tallest skyscrapers in 3 categories. There's plain tall, up to about 1,000 feet or the size of New York's Chrysler Building. Super tall, buildings over 1,000 feet. And mega tall, buildings over 2,000 feet or the size of the Mecca, Saudi Arabia clock tower. As of 2020, there are only 2 other mega talls, the Shanghai Tower at 2,073 feet and Dubai's Burj Khalifa at a staggering 2,700 feet. That's more than twice as tall as the Empire State Building.
I often get asked, what are the biggest barriers to how tall we can go? And there's only one barrier, and it's not technological. It's financial. It's who is gonna pay for it.
Some of the very tallest buildings are designed to bring tourists and prestige to the cities they tower over. But most building owners aren't seeking height records. They're seeking profits.
To build the tallest building in the world is not necessarily to build the world's most profitable building.
That tall buildings can be good investments is evidenced by the number of cranes sprouting up in many major cities. Their proliferation also seems to indicate that few people question tall building safety or think twice about living or working in one. And for the most part, tall buildings do have stellar safety records. But engineers and designers are not infallible. And some threats can be unpredictable and difficult to overcome, like fires. Although most fires occur in homes and low-rise apartment buildings, frightening skyscraper fires do happen, as recent blazes in China and Dubai so clearly demonstrate. In the U.S.,
fire started on the 12th floor of the Interstate Bank Tower.
Huge multi-story skyscraper blazes are fairly rare. But fires in mid-sized buildings, especially older apartment-type blocks lacking basic fire safety requirements, are an ongoing concern. An egregious recent example of this problem occurred overseas at the 24-story Grenfell Tower in London. The fire started in a kitchen where flames shot out a window, igniting the building's highly flammable exterior wall covering, or cladding. Because of this danger, flammable cladding is prohibited in the US, but not at the time in the UK. Although cladding was the main culprit, the building also lacked fire alarms and a system to communicate with the residents. There were no sprinklers and just one exit stairway that would eventually fill with smoke. As a result, more than 70 people died, making Grenfell everyone's nightmare of a tall building blaze. And unfortunately, Grenfell-like safety flaws exist in many U.S. cities, particularly with older apartment buildings, like these in New York.
We have a significant number of housing projects and buildings that are, 20 stories. The code doesn't require alarm systems. The code doesn't require sprinkler systems.
As with Grenfell, the main deficiency in these buildings is communications.
There's no public address system necessarily in the older existing buildings. The only information they can gather is looking up for signs of smoke or flame. And the occupants are left really to their own devices in terms of figuring out what to do.
At Grenfell, this proved fatal because many residents followed the one instruction they were given: stay put unless instructed to leave.
In Grenfell, the guidance that had been given to residents of those buildings across the city was that you should stay in place in a high-rise residential fire unless you're immediately threatened.
But with no communication system, by the time leaving became obvious, for many, it was too late. This shelter-in-place guidance is widely recommended in the U.S. as well.
It seems counterintuitive to stay in the building, but you really are safer if there's no fire in your apartment, because to leave and go through the hallway where there's going to be smoke, you're really exposing yourself to danger.
The problem is people don't have the expertise to evaluate if there's smoke in their hallway. Is it heavy smoke? Is it incidental to a fire? They don't know. So they are left and immediately put into a position of great anxiety. And so sooner or later, some of them are going to say, the heck with this, I'm going to try to get out of here.
And once in an exit stairway, there could be even greater danger.
What may appear to be a clear stairwell on your floor may be contaminated with smoke at a lower level. People die in stairwells trying to evacuate fires.
And many stairwells are narrow, creating a dangerous bottleneck for firefighters trying to reach and control the blaze.
We do have some narrow stairways, so either the people coming down are going to get held up or the firefighters going up are going to be slowed down.
Adding to this challenge is how to get elderly or disabled people down to safety.
That becomes a problem if we have to take them down. That's very intensive to move somebody down the stairs. And that's why our best advice is we want them to shelter in place in their apartments.
Elevators could help, but they can spread fire or smoke, and people can get trapped inside. So occupants are generally restricted from using them. A new generation of fire-safe elevators is starting to come online, and these would certainly help the aged or disabled. They are housed in special closed-door areas, pressurized to keep smoke out, and there are drains to keep water out. They hold great promise. But there are so few operating in the U.S., they have yet to be fully fire-tested.
So we don't know the effectiveness of those elevators until they're actually used in an emergency situation.
But there is a proven technology that can avoid the need for elevators by keeping most fires from spreading. That sprinklers have the capacity to save lives and buildings has been proven time and again, even at high-profile addresses. A recent fire in Trump Tower, New York, built before sprinklers became mandatory there, resulted in the death of a resident and several injured firefighters. Sprinklers could have prevented these casualties. So why don't more buildings have them?
And the reason we don't have sprinklers in all tall buildings is because the real estate industry doesn't want to spend the money to put them in.
The good news is, sprinklers are now mandatory in most recently built tall buildings. And these have helped keep fires and fire-related fatalities on the decline. But fires aren't the only threats to tall buildings and their occupants. Despite a mostly excellent safety record,
Everyone get back, get back!
engineering or construction mistakes do happen.
Oh my God.
And when they do, the results can be terrifying. This is San Francisco's Millennium Tower, a 58-story luxury condominium that became a much sought-after address when it first opened about a decade ago. But in 2016, the news broke that it was sinking and tilting.
This 58-story downtown high-rise unexpectedly sunk 16 inches. This golf ball rolling down the uneven floor toward the direction the building is leaning.
The revelation came as a shock to condo owners.
The building was still settling vertically and horizontally, and it was unclear when that would stop. Some people, I think, just left. There was a concern that the building was about to topple over.
And in a city with a history of earthquakes, this was especially worrisome. Today, the so-called Leaning Tower of San Francisco has sunk about 18 inches on its northwest corner. When the news broke, Ron Hamburger, a veteran structural engineer, was hired by the building's developers to find out why the Millennium was sinking and if it could be stopped.
The Millennium Tower basically is sinking because it's a taller building and a heavier building than most of the other buildings that have been constructed in San Francisco. It imposed greater weight on these sand layer that exists about 80 feet below the sidewalk.
Like many cities bordering water, San Francisco rests atop ancient layers of soft sand and clay. Whereas in New York, a hard bedrock-type layer called schist lies close to the surface in many places, so anchoring tall buildings here is ideal. But in San Francisco, bedrock lies deep below the surface, and reaching it with supporting piles is difficult and expensive. So tall buildings are often placed on concrete mats with piles that don't go to bedrock. But the piles do transmit the building's weight through the weak upper soil layers to deeper, firmer layers, and the system normally works quite well. But for some reason, the Millennium's extreme weight pushed down with enough force to compress the soil under some of the piles, causing the building to settle unevenly. The tower's owners claim a neighboring construction project called the Trans-Bay Terminal contributed to the uneven settling by dewatering the soil under the Millennium.
The dewatering is done in order to have a dry excavation so that you can actually build what you want to build.
Whether the fault was dewatering or poor engineering, the sinking has slowed to about 1/4 inch a year and could stop entirely. Regardless, Ron Hamburger is now heading up a multi-million-dollar foundation fix that will shore up the building by extending the concrete foundation mat on the sinking corner and adding additional supporting piles that go all the way to bedrock. It is hoped that the fix will allay public fears about the building's stability. The Millennium Saga stands out in part because serious mistakes in high-profile buildings are rare. Their engineers have consistently produced structures that stand straight, can support their own weight, and are capable of resisting a constant threat to any tall building: the force of the wind. Although no tall buildings of note have ever been blown over, another famous mistake almost brought that frightening prospect to New York. When it was completed in 1977, the now modest 59-story Citicorp Center was the 9th tallest building in the world. With its aluminum and glass exterior, Citicorp was among a new generation of lighter skyscrapers that avoided the expense of heavier masonry-clad facades, like the Empire State Building. But lighter buildings can sway in the wind, and when they do, people inside often complain about feeling motion sickness. To counter the sway at Citicorp, the building's engineer, William LeMessurier, had New York's first tuned mass damper installed near the top of the building. It is basically a 400-ton block of concrete that slides on a bed of oil. When wind pushes against the outside of the building, the giant block will slide in the direction of the sway. Large piston-like devices restrain the block, absorbing the energy and slowing its movement. This makes the block lag behind the moving building, which in effect counters the sway and keeps the building steady. Without dampers, tall buildings like these beanstalk-thin luxury condos could be fairly uncomfortable to live in.
The building can't have the reputation of having the kind of proverbial waves in the toilet where you can feel the building moving, because people then feel uncomfortable. They won't buy an apartment where they feel vulnerable.
Back at Citicorp, the resourceful LeMessurier solved another problem. He raised the building above the street and placed its 4 major support columns under its sides, rather than at the corners, as is typical. He did this to accommodate a church. Not this modern one, but an older one that had become dilapidated. So the church struck a deal. They would get a new building in exchange for letting Citicorp rise above it. But some engineers were skeptical of its radical design.
I got a telephone call from a student who was assigned to write a paper on this building by his professor. The professor had said there was something funny about this building because the columns were not in the corners like they ought to be.
Under the facade, LeMessurier placed a series of V-shaped steel braces that channel wind and gravity forces diagonally to the columns. He was confident his radical design would work because computer models and wind tunnel tests showed that it would. Engineers wind test building models to see, among other things, if their shape produces a dangerous phenomenon called a vortex. The model is bolted to a base that contains sensors underneath, and when the fans come on, the sensors measure the model's response to the air flowing around it.
One of the issues with tall buildings is called vortex shedding. As wind goes past an object, it'll go first to one side and then the other. And when it does this, it'll create little swirls in the air.
Vortex shedding creates whirlpools that lower the air pressure behind a building. Now, when the wind hits the building, it can push it and make it sway rhythmically, like a child on a swing.
At first, they kick their feet just randomly and the swing goes nowhere. You have to teach them that they have to kick their feet at the natural harmonics of the swing. So in a tall building, it's the same thing.
Buildings that gain momentum like a swing put dangerous pressure on structural connections. But changing the building's shape can disrupt wind forces and stop the buildup of vortices.
Sometimes a very small change can be the difference between a building being successful or not successful.
Citicorp passed its wind tests, but about a year after it was occupied, LeMessurier discovered that winds striking the building diagonally, rather than face on, could increase the stress on some of the V-braces by 40% or more. Then he realized that during construction, his office had permitted contractors to bolt the braces together instead of welding them, as he had originally specified. He calculated that winds in excess of 70 miles per hour, striking the corners of the building, could sever the bolted connections.
I came to the conclusion that a storm which had a probability of occurring once in 16 years would cause the building to fail and collapse. I can't live with that.
LeMessurier recommended welding 6-foot-long steel plates on either side of the bolted connections to strengthen them. This would certainly solve the problem, but would take weeks to finish. So as workmen began the arduous task,
folks, get on the sidewalk, please.
The city drew up emergency evacuation plans.
Not only would they evacuate the building, but they would evacuate a 10-square block area around the building just in case the building falls over. Can you imagine?
And as fate would have it, in late August 1978, Hurricane Ella began heading for New York. As its winds intensified to over 100 miles per hour, the disaster LeMessurier feared loomed closer, and there was no way repairs could be completed in time. But instead of tracking toward the city, Ella veered out to sea.
It all ultimately worked out, but it was a very dangerous situation.
Despite the travails of Citicorp, tall buildings have proven time and again that they can successfully withstand the most extreme weather conditions. And they are also engineered to withstand another major force of nature. But when it comes to earthquakes, the prospects that some tall buildings may not survive is a very real probability indeed. It's been over 30 years since the 1989 Loma Prieta earthquake in San Francisco.
Shut off the gas! Shut off electricity! Store water!
The quake caused major damage to houses and infrastructure near the bay. But the rest of the city, including tall buildings downtown, escaped relatively unscathed. That's because the quake originated 60 miles from the city, and more importantly, was not another big one. In 1906, a giant earthquake on the San Andreas Fault and devastating fires that ensued basically destroyed the city. The U.S. Geological Survey now says there's a 70% chance another powerful quake will strike the region sometime within the next 30 years.
The earthquake could occur now, it could occur in 20 years, but it's not going to wait 100 years.
There are 7 major faults in the Bay Area, with the most worrisome being San Andreas and the Hayward.
We're in a parking lot south of downtown Hayward, California. You can see donuts, tire tracks that kids have made.
David Schwartz, a recently retired USGS seismologist, has studied the Hayward Fault for years.
And as you're crossing the parking lot, you look down and you see the asphalt is sort of disturbed. There's a little step across it here. There's a whole series of cracks here. This is the Hayward Fault. And the fault is creeping. It's actually moving slowly all the time. And it produces this type of feature. When you come to here, these older buildings, this separation expresses creep along the fault, This building is moving towards me. This building is moving away. When the fall finally decides to move in its big earthquake, I really wouldn't want to be standing against one of these buildings. In the end, the fault always wins.
The fault travels northwest from the town of Hayward, through Oakland and the Berkeley Hills, where millions of people live on or right next to it. And the force of a big quake could readily travel across the bay, smack into downtown San Francisco, bringing with it the potential for a major disaster. And when this earthquake strikes, it's pretty clear what types of buildings would likely suffer the most damage.
The worst performing buildings are what we call unreinforced masonry buildings. These are typically either common red brick buildings or sometimes stone buildings. The masonry is quite strong, but it's also very brittle. And under the effects of severe ground shaking, the masonry will crack and crumble. And it's very common actually for the walls to fall away, creating not only a hazard for people in the building, but also people outside the building.
Because masonry buildings could be vulnerable to collapse, it was deemed safer to construct tall buildings with steel frames.
Steel seemed like the perfect choice because if you push on steel way beyond its strength, the steel bends instead of breaking, and therefore you wouldn't collapse the building.
And by the 1960s, the preferred method for joining the pieces in a steel frame was to weld them together. What engineers call welded steel moment frames were deemed one of the safest designs for tall buildings in California. That thinking would get a severe jolt after the 1994 Northridge earthquake.
You can see extensive damage here.
The 6.7 temblor struck densely populated suburban Los Angeles, causing scores of deaths and property losses in the billions. It also revealed a serious flaw in supposedly safer moment frame buildings.
When the Northridge earthquake occurred, a number of these buildings experienced unanticipated fractures, cracking of the steel connections between the beams and the columns.
Outside, most of the buildings looked stable. But inside, inspectors found weld failures and cracks in the steel. Now the question was, what could happen to these steel frame buildings in an even stronger earthquake? Swaminathan Krishnan is a structural engineer specializing in computer simulations. After Northridge, he modeled a specific moment frame building damaged in that quake and subjected it to the force of a stronger San Andreas earthquake.
In particular, we wanted to see whether this building would remain standing or would it collapse.
As the big quake begins to spread, his program assesses its effect on the building's frame.
This building does fine for a while. You can see, that it's going back and forth and it's coming back and staying vertical. But at some point, there are several connections that break inside of the building and the building comes crashing down.
Although improved materials and welding techniques have made newer steel buildings far less susceptible to failures, older moment frames, including the famous Transamerica Pyramid and other buildings throughout California, remain unfixed and could even have become weakened by previous quakes.
So if a building goes through an earthquake, even if it is apparently undamaged, it's used up some of its original earthquake-resisting capability.
The problem is right now there are hundreds of tall buildings of that kind. They've not been opened up and they have not been retrofitted.
And if a big earthquake comes,
we are going to see building collapses. That is what our modeling tells us.
A few moment frame buildings have been retrofitted, but a big deterrent is cost. To remove interior walls and ceilings to inspect connections, much less tear things apart and fix those connections, can be extremely expensive and may just be unnecessary. In 1985, a powerful earthquake struck Mexico City, where taller buildings saw relatively little damage. But many mid-size, 10 to 20-story buildings were tremendously damaged or totally destroyed. That's because their particular height resonated with the shock waves from this earthquake.
Resonance is a phenomenon that occurs when the natural frequency of a structure closely matches the natural frequency of an exciting force.
Earthquakes send out vibrations of various wavelengths or frequencies. When they reach a cluster of buildings, those that suffer damage are often the ones whose height best matches those particular frequencies.
When the ground shaking has in it high frequencies, meaning if the shaking is jarring, it's going to go do this, boom, 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 boom. That kind of shaking will selectively affect short buildings.
Whereas longer wavelengths can cause tall buildings to sway rhythmically, and in extreme cases, can collapse them. Other factors, such as soil conditions or inadequate construction materials, can also make tall buildings vulnerable. But there's no factor more important to an earthquake's destructive potential than location.
So absolutely, your distance from the fault is one of the most important things about what shaking you receive.
In 1995, one of the most devastating earthquakes in the modern era struck Kobe, Japan, along a fault that lay close to the city. 6,000 people died, tens of thousands were left homeless, hundreds of thousands of buildings of all sizes were damaged or destroyed.
There were collapse of buildings and there were collapse of steel frame buildings from the same problem with welds that we saw in the Northridge earthquake.
Kobe's proximity to a fault, as well as its large concentration of people and buildings, raises an obvious question. Could this be the fate that awaits cities like San Francisco?
I think about risk for a living.
Ibrahim Al-Mufti, Ibi to his friends, is a structural engineer who's worried about his city's fate.
You know, I walk to work through downtown every day, looking up at the buildings, and I know too much in a sense. It is definitely possible that a few buildings may come down in a big earthquake.
Ibi's goal is to engineer a building that will be among the safest ever built, even reaching beyond standard building codes.
The building code objective for many years has always been life safety, to protect it against full collapse.
Recent earthquakes in Christchurch, New Zealand, demonstrate the flaw in life safety codes. Many heavily impacted buildings did not collapse, and therefore saved lives. But most were so severely damaged, they could not be reoccupied and had to be torn down, which has depopulated the city and derailed it economically.
And actually, Christchurch, you could argue, is still recovering from that earthquake 10 years ago. And so I always ask the question, are we as engineers bringing our knowledge to bear on designing these buildings to be more resilient and allowing these cities to recover more quickly after big earthquakes?
San Francisco City Administrator Naomi Kelly is hoping to make tall building resiliency one of the city's top priorities.
Downtown San Francisco is our economic engine for the city. We have now 62 tall buildings. Many more people are living downtown. And so we are now looking at not just the building codes where the building's good enough for you to get out the building, but how do we make our buildings more resilient, and how fast can we reoccupy those buildings? Most folks want to not only just survive the earthquake, but they want to get back into their home or office building as soon as possible.
And that's exactly what Ibby and the engineering team for 181 Fremont set out to do.
They're triangulating, right? All of those forces have to be.
Located near the Millennium and Salesforce Towers, 181 Fremont is 56 stories tall, slim, and angular. The visionary structure owes its design to Jeffrey Heller. As a young architect, Heller had gone to Armenia in 1988, where he saw firsthand the devastation inflicted by a huge earthquake.
What really got me was the level of desolation and devastation. What we saw was in the town of Spitak, which was the epicenter of the earthquake, a city of 25,000 gone, nothing left.
Over the years, Heller designed several earthquake-resistant buildings, but 181 was for him the commission of a lifetime.
The building had to be great, or at least the best I could do. 181 is 800 feet tall. 2/3 of it is office, about 45 floors. And then the top 1/3 is residential.
The views from inside the upper floor apartments are nothing less than spectacular, as are the appointments in its luxurious penthouses. Architecturally, the building's most defining feature is its striking exoskeleton, with long braces that help support the entire building, thereby opening up interior spaces.
It leaves the interior of the building completely free up to the core of any vertical support at all.
The exoskeleton is key to the building's ability to manage earthquake and wind forces.
So if you look at the building from the outside, you'll see these diagonals that are connected to the columns. And at the corner connection, we've introduced dampers on the ends of the braces that basically act as giant shock absorbers.
As the building flexes, the middle brace stretches or shortens. When it does, secondary braces activate the dampers that compress and stretch like springs, absorbing energy and channeling the force of these movements to the main columns. At the base of the columns, we see they can lift up incrementally. So in an earthquake, the building acts, as Ibby notes, like a skier with ski poles.
And so you've got these columns that are acting like ski poles in a sense, and some lift up, and you've got more pressure on this one to stabilize yourself, and as you go this way, same thing.
The overall design is so unique, it earned 181 a first.
We actually received the world's first Ready Gold rating, which means that we've designed it in a certain way such that building occupants can get back and use the building almost immediately after a very big shake.
This is something some seismic experts have been advocating for.
We are trying to change the building code to say life safety is not enough. We need functional recovery, meaning I can recover the function of the building in a reasonable amount of time.
But resiliency features like those on 181 can be expensive. So until they are mandated in building codes, getting developers to incorporate them may be a challenge.
It would be wonderful if American building owners and developers wanted to provide society buildings that were more resilient. But for the present, it seems it will take government to force that. Or an earthquake. If we had a major earthquake and it caused catastrophic damage similar to what New Orleans saw in Katrina, that might be enough to change society's attitudes and foster an era when we do indeed develop more resilient construction.
If we have the will to apply lessons learned, tall buildings will continue to become better at withstanding earthquakes, wind, or fire. And this is certainly critical, since going up is just about the only solution to urban population density. But beside becoming safer, what else could tall buildings become? What other considerations might go into their planning and design? For decades, visionary thinkers have proposed making tall buildings more like eco-friendly, vertical villages. Although some of these designs are, well, a little bizarre, they generally promote light-filled, open, communal spaces that can make buildings more people-friendly. And today, some designers are reaching for that vision with a less fantastic, but still vibrantly creative, tall building environment. This bustling atrium is office central for Bloomberg LP, the global business, financial, and communications giant. The first thing you notice in this building is all the stairs, and people constantly on the move. The elevators stop on every floor, only for disabled people. For everyone else,
the elevators, in fact, only stop on 9 out of the 25 floors that we occupy.
The stair-stepping helps promote employee fitness and is just one of the out-of-the-box concepts in this building's overall design. The offices are in the lower half of a tall residential tower and in a smaller building connected to the tower by a dramatically curved multi-use space. Its lead architect is Raphael Pelli.
There's a theatrical quality that I hadn't anticipated as much as it truly is.
In addition to this active, light-filled atrium, the rest of the offices are also atypical.
The company wanted a different model for organizing office buildings than the traditional historical one, where you stacked a bunch of very isolated units on many, many floors, making a very siloed environment. Instead of that, they wanted fewer floors, very big floors, all connected around a central space.
That central space is called the pantry, for obvious reasons. It looks more like a public space than a corporate office. The openness and informality clearly encourages employees to meet and exchange ideas.
You'll be grabbing a cup of coffee and you'll see 10 people that you need to catch up with. And it's a great way of getting work done.
Oh, I haven't seen you in so long. We need to catch up. I got something I need to tell you. And by the way, do you have 5 minutes now? Because we'll grab a coffee and stand around one of the pods.
We wanted the sixth floor central space to be the beating heart of what Bloomberg wanted to be.
There are no closed-door offices here. Meeting rooms have glass walls.
So it was all done to be transparent. Everybody could see what's going on.
As part of what the company calls its Fitwell program, beside all the stairs, there are several outdoor decks where people can get fresh air. And keeping with its Green Buildings initiative, near JFK Airport in Queens, the company has financed a solar array that generates over 1.5 million kilowatts of sustainable energy a year. That's about 5% of its power use. Many of the concepts, like encouraging bike riding, as well as the free snacks and open interior spaces, are not new. They're borrowed from Silicon Valley companies like Google. But these companies are in low-rise buildings, in roomy, open spaces. Whereas incorporating these design considerations in a tall building environment breaks the mold on how these buildings can be reimagined.
The energy, the environment, it's just an amazing building.
As more and more skyscrapers, office and residential, come to dominate our cities, ultimately, what will this mean for our future?
I think the skyscraper makes sense in the future of the city because it does use land efficiently. And that's a more sustainable way to live on the land. It's a smarter way to build a future city that consumes less energy, that accommodates the lifestyle amenities for many more people than if we have to spread out.
Tall buildings are a huge part of the answer to the challenges that face us today: social, economic, climate change, urbanization, population growth. But they are only several baby steps along the path they need to tread to truly deliver on that potential. The buildings need to do the very best that they can do if we want to carry on living on this planet.
You're watching PBS.